everyone, this is the Class 5 video lecture for PH 125, and today we'll be talking about acceleration and the constant acceleration equations of motion. So let's get started with a quick review. We've been talking about one-dimensional kinematics, and we started with three measures of length: position, distance, and displacement. So remember, position is the location relative to a defined coordinate system. So for example, in the bottom here, I have my positions labeled in green as locations on an x-axis. Next, we talked about distance. Distance is the total length of travel. And so on the diagram at the bottom here, I would say that the distance is the total length of the two blue lines added together. So that would be the total length of travel. And then next up, we have displacement. Displacement is change in position. And so on our graph at the bottom, that's represented by this orange arrow that points from initial position to final position, and that is our displacement. So position and displacement, they're both vectors. Their directions are given by signs, plus or minus signs, in one dimension. And distance is a scalar, which means it's always going to be positive. All three of these measurements are, they have dimensions of length, which means in SI units we'll be using meters. Okay, next we talked about speed and velocity. So remember, velocity is the rate at which position changes, and so it has dimensions then of length divided by time, which corresponds to SI units of meters per second. Velocity is a vector, which means it has magnitude and direction. Again, the direction is given by plus or minus signs in one dimension. And we remember from last class that this velocity is related to the slope of an x versus t, or position versus time graph. Okay, so we talked about two different types of velocity. We talked about average velocity, which we denote v average. It's displacement over time. Remember, displacement, that was delta x divided by elapsed time, so that would be delta t. We remember that delta just means change in. Okay. And so it's always going to be final minus initial. So that means V average is x final minus x initial over t final minus t initial. And this was exactly corresponded to the slope of a line connecting 2 points on a position versus time graph, the 2 points that correspond to t initial and t final, right? So if I look at my graph at the top of the screen here, my t initial would be here at about 10 seconds, and t final would be over here at 30 seconds. So I drew in my corresponding points on my graph, and then I went ahead and drew a straight line between them. And that straight line between them has a slope that's equal to the rise over the run. The rise in this case would be the change in position, delta x, or the displacement, and the run would be the elapsed time, delta t. So that means that the slope is delta x over delta t, which we can see is exactly equal to the average velocity from our definition. Okay, and then we also know that the average speed is not the same thing as the average velocity. So it's really hard. I will slip up, I'm sure. So we tend to interchange these words speed and velocity, but they really have distinct meanings. So velocity is always referring to the displacement over the change in time, whereas speed refers to distance over change in time. And displacement and distance do not generally have the same magnitudes. So the classic, or an example of that, if you go back a slide, remember the distance traveled by our little stick figure was not the same as the magnitude of his displacement. And so these two quantities in general will not be equal to each other. Okay. Next, we talked about instantaneous velocity. So instantaneous velocity, we'll often just say velocity when we mean instantaneous velocity, and it is the speed at a particular, it's the velocity, see, I already did it. It's the velocity at a particular moment in time. Okay, and so how do we calculate it? Well, mathematically, we use this equation. It's exactly the same as the average velocity equation, but we just make sure that that change in time, the elapsed time, it's really short. So we're only looking at one quick moment in time. So the way we write that mathematically is just the limit as delta t goes to 0. Okay, and so then this can also be interpreted from a position versus time graph. So now I've picked some new time. It looks like it's about 60 seconds here. So I would say that this is my time of interest here. And so then I drew a point on my graph that corresponded to that point of interest. And I drew in the tangent to the graph at that moment in time. And then remember the slope of the tangent to the curve, which is that yellow line there, that corresponds to the instantaneous speed right at that moment in time. So instantaneous speed, slope of the tangent, average speed is the slope of the line connecting the 2 points over which you want to take the time average for that speed. Okay. And now it is okay actually to think about the magnitude of the velocity being equal to the instantaneous speed. And that's because the direction over one moment in time, the direction isn't going to change. And since the direction isn't changing, that will tell us that the distance is actually over that one moment in time, the distance traveled in one quick moment. It's going to be the same thing as the displacement in that one quick moment. And so that's why when we think about instantaneous velocity, its magnitude is exactly equal then to the instantaneous speed. Okay. All right, so that was it for the velocity and speed. And so then the last thing that we'll talk about in this kinematics section is acceleration. So we introduced it quickly at the end of last video, and we're going to spend quite a bit more time on it today. So acceleration tells us how quickly velocity is changing. So remember, the velocity told us how quickly the position was changing, and now acceleration is telling us how quickly the velocity is changing. Okay. So we can define, just like the velocity, we're going to define an average acceleration and an instantaneous acceleration. So average acceleration is just change in velocity over elapsed time. Change in, remember, that's that delta. So that tells me that I'm looking for delta V in this case, change in velocity. Or in other words, V final minus V initial, and then I'm dividing by the elapsed time between that, the measurement of that initial velocity and the measurement of that final velocity. So that's what that delta T corresponds to. We could also then take that delta T, that elapsed time between our two velocity measurements, and make it go really small, and that would tell us the instantaneous velocity, the instantaneous acceleration. And that's because acceleration can be changing, just like the velocity can be changing. And so your average acceleration might not be equal to your instantaneous acceleration. The only time those two things would be equal would be if you have constant acceleration. All right, and so then our definition of instantaneous acceleration looks a lot like the definition of instantaneous velocity. We have this limit as delta T goes to 0 of the change in velocity over elapsed time. Okay, so a few more things about acceleration. Remember, it has dimensions of length divided by time squared, and that's because velocity is length divided by time, and then we're dividing by time again, right? So that gives us length divided by time squared. In SI units, this is going to correspond to meters per second squared. Okay, and it is a vector, which means that in one dimension, we're going to characterize its direction by plus or minus signs. You'll always need to include both direction and magnitude of the acceleration. And then two things that we're going to talk about today that we didn't quite get to in the last video lecture. It turns out that the direction of the acceleration is the same as the direction of the change in velocity. So it's not necessarily the same as the direction of the velocity, it's the same as the direction of the change in velocity. So we're going to spend a bit of time on that. And then we're also going to spend some time thinking about how to relate the acceleration to velocity versus time curves. And it turns out that the acceleration is just the slope of a velocity versus time curve. Okay, so now let's do a quick little practice problem working with displacement, velocity, and acceleration. So a car moves from a position of plus 4 meters to a position of minus 1 meter in 2 seconds. And the initial velocity of the car is minus 3 meters per second, while the final velocity is minus 1.5 meters per second. So the first question we want to answer is, what is the displacement of the car? Well, first thing I'm going to do is I always like to write down the things that I'm given, and here I'm going to assign them to different variables so I can keep track of what's happening in this problem. So I notice here I am told the car moves from a position of 4.0 meters. So that tells me that this guy, this 4.0 meters, that should be my initial position. It's moving from that position to a position of -1 meters, and so that would be my final position in 2 seconds. So that 2 seconds, that's going to be the amount of time that elapses between my measurement of my initial position and my final. So in our equations, that's been delta t. Okay, the initial velocity, well, that's easy. It's telling me exactly what that is. So that's going to be my initial velocity is -3 meters per second. And the final velocity, again, it's telling us exactly what that is. So that's v final is equal to -1.5 meters per second. So I could go ahead and summarize that in a little table of things that I know, and then I can calculate my given quantities. So let's start with the displacement of the car. Displacement, remember, is delta x, change in position. Delta always means final minus initial. So I would go ahead and say my final position is -1 meters. We have to include those signs, right, because it's a vector, and so we have to think about direction here. So -1 meters for my final position minus my initial position, which was +4 meters. -1 minus 4 gives me -5. So my displacement is -5 meters. Okay, next we want to calculate the average velocity of the car. So average velocity, remember, was displacement over time. And so I already calculated my displacement, that was from part A. And so then I just need to think about the elapsed time, which I already wrote down was 2 seconds. And that's between my, initial and final positions as measured. So I would say that V average is my displacement -5 meters divided by 2 seconds. And that's just going to be -2.5 meters per second. So that velocity, average velocity, is motion in the negative x direction, which traditionally we would say is to the left. Okay, last one, what is the average acceleration? So remember, average acceleration is defined as the change in velocity over the change in time, the elapsed time. So our velocity was measured over that 2-second time interval, right? So the initial velocity was measured at the beginning, and then the final velocity was measured 2 seconds later. So I would say that my average acceleration over that time frame, that 2-second time frame, would be -1.5 meters per second. That was my final velocity. Minus 3 meters per second, right? So that was my initial. Again, we have to include all of our signs here. 2 minus signs in a row, those cancel and give me a plus sign. So -1.5 plus 3, that gives me 1.5, and then I have to divide by 2. So I got 0.75 meters per second squared, and that's positive. So the acceleration is in the positive x direction. Okay, all right. And so now let's take a closer look at interpreting the direction of the acceleration. So acceleration, change in velocity over elapsed time. This is really the average acceleration here. I should probably specify. It would only be instantaneous acceleration if that delta t was really small, or if we had a case where we had constant acceleration and those two things were equal to each other. Okay, and so interpreting the sign of the direction of the acceleration can be a little bit tricky. Because we want to think about the acceleration oftentimes as being in the same direction as the velocity, but really it's the change in velocity. And so that can be a little bit tricky sometimes. And it's specifically thinking about what's happening to the velocity for a given acceleration. Okay, so there are 2 cases to think about here. The first case is when the acceleration has the same sign, the same direction as both your initial and final speed velocities. Then we would say that the speed, which is the magnitude of that instantaneous velocity, that speed is increasing. So the magnitude of your speeds is getting bigger. Your final is bigger than the initial. So let's look at 2 cases for that. First case, think about it, you have the car is moving in the plus x direction, both at your initial time and your final time. So both times the car is moving in the positive x direction. If the car is also accelerating in the positive x direction, then we would expect the velocity to be getting bigger in that positive direction. So the magnitude of V final would be bigger than the magnitude of V initial. All right, another way that we could have this case happening where we have the velocities and the acceleration in the same direction would be if everything was pointing in the negative x direction. So what if my car initially was moving in the negative x direction, finally it was moving in the negative x direction, and also the acceleration was in that negative x direction? Well, then in that case, we would be having getting a more negative value for our final velocity. So it would be increasingly negative, which means that it would have a bigger magnitude at that final time than at the initial time. And so again, we would say the speed is increasing because it's becoming a bigger negative number. Okay, so it's a little bit counterintuitive there. All right, let's look at the second case here. And this would be if our acceleration has the opposite sign compared to the initial and final velocities. In that case, we expect that the speed will be decreasing, which in other words would mean like the car is slowing down in a particular direction. Colloquially, you would say that this means that the car is decelerating. Okay, so again, we have two ways that this can happen. So what if, again, our car, it has a velocity in the positive x direction, both at initial and final times, but our acceleration is in the negative x direction? Well, in that case, that would be like the car would be slowing down, and so its velocity would be getting less positive. So that final velocity would have a smaller magnitude than the initial velocity. Alternatively, we could have the case where our car was initially moving to the left, which means that its velocity was pointing to the left, well, in the negative x direction. Well, if its acceleration is in the positive x direction, then we would have the same sort of thing happening where the initial velocity would have a bigger magnitude than the final velocity. So the final velocity would be getting smaller and smaller since those two things are acting in opposite directions. And so what that would mean is that the velocity is getting less negative. It has a smaller final magnitude, and so again, we would say that the car is slowing down or decelerating. So this is the case that gets a little, I think, tricky, because decelerating, you might want to think, oh, acceleration is negative, but the negative has to do with the sign of the acceleration, the direction of the acceleration. It doesn't have to do with the magnitude of the speeds, right? So here I have a positive acceleration even though the car is slowing down. Okay, so we want to just try to separate those two things from each other. We want to think about the direction of the acceleration as separate from what's happening to the speed of the car. Okay. And next up is the second topic for acceleration today, which is how to read acceleration from velocity versus time plots. So to get there, we're just going to remember that when we had a position versus time plot, like in my top figure here, we were able to calculate the average velocity as the displacement delta x over delta t, right? And so that was the slope of the line that connected the 2 points at t initial. So my t initial would be like here, t initial and t final on my position versus time curve. Okay, and then we said that the instantaneous speed was really the slope of the tangent to the curve at a given time. So my time of interest right here, I would say that I could draw in a tangent to the curve at that point in time, and then my instantaneous velocity would be the slope of the tangent to the curve at that moment in time. Okay, so looking at the definition of V average and comparing it to the definition of A average, what I could say is that if I have a velocity versus time curve rather than a position versus time curve, I would expect that the average acceleration would just be equal to the slope of the line connecting the 2 points, the initial and final time points on my velocity versus time curve, because I can see right here, my average acceleration is delta V, which would be like the rise, divided by delta T, which would be like the run, right? And so that tells me that I have average acceleration that's just equal to the slope of the line connecting my initial and final time points on my v versus t curve. Okay, and then similarly, I could think about, okay, what if I want to know the instantaneous acceleration at some moment in time t? Well, I could draw in the tangent to the curve at that time point. And then I would find that the slope of that tangent to the curve is just exactly equal to the instantaneous acceleration right at that moment in time. Okay, so now just a quick question to try to, compute that information. Now we want to match the car to the appropriate v versus t curve. So here you'll want to be thinking about both of the pieces of information we learned today. What happens when our acceleration and our velocity are in opposite directions? And then also, how do we tell what's happening to our how do we tell acceleration based on a velocity versus time curve, which is what we're shown here. Okay, so let's see how we could answer this problem. First of all, I would say that the positive x direction is to the right, which means that looking at my two arrows, the velocity arrow is pointing right, and so my velocity is positive. And then I would say that my acceleration arrow, the purple arrow, is pointing left, which means that my acceleration is negative. So I need to find something on one of these four green lines that corresponds to a positive initial velocity and a negative acceleration. So positive velocity means it would have to be above v equals 0 on my position versus time curve. So that immediately eliminates C and D since they have negative velocities. Next, I want to think about negative acceleration. So what does negative acceleration tell me? Well, it tells me that I must have a negative slope. So which one of these two has a negative slope? I would say V has a negative slope, and so that would mean that my answer must be B. Okay. And so actually we can get some extra information out of these V versus T plots. It turns out that they will also tell us something about displacement. So these are really useful plots. We can learn about velocity, of course, as a function of time, but also acceleration and displacement. So to see how these plots are related to displacement, we're just going to do a quick example together. So you're driving on the highway and you're driving at a constant velocity of 60 miles per hour east. So we'll say that that's the positive direction, positive x direction. And you do this for 15 minutes. Then it's time to take your exit, so you slow down for 1 minute. And you're slowing down at a constant rate. You decelerate at a constant rate. Okay, and so what we want to do first is sketch the resulting velocity versus time graph. So we have to pick out some key pieces of information. So first of all, for the first 15 minutes, we're traveling at a constant velocity, right, of 60 miles per hour. And so that tells me for the first 15 minutes, so up until t equals 15 here, right? So up until, I'll just draw a little star. Up until t equals 15 minutes, we're traveling at constant velocity, which means that I would be expecting a horizontal line right at my velocity of 60 miles per hour, which in terms of miles per minute is 1 mile per minute. That's what I have as the units of my graph here. So I would expect a straight line at 1 mile per minute. Okay, so that's the first part. The second part is that we are decelerating at a constant rate. And so what's that really telling me? That tells me that my acceleration is constant. And since I'm slowing down and my velocity was initially in the positive x direction, my acceleration must be in the opposite direction, which tells me in this case the acceleration should be negative. Okay, so the last part of my velocity versus time curve then is going to be a straight line. Again, it has constant slope, right, because I have constant acceleration, and it's going to be a downhill line, right, so it should have negative slope. All right, and it should last 1 extra minute. So that means my final time is going to be right here at 16 minutes. Okay, So let's draw that in, a straight line with constant slope and constant negative slope towards 1 minute. We're ending with a velocity of 0, so we're coming to a stop. Okay, so that's everything I need to sketch my velocity versus time graph. Next up, we want to know how far did we drive during the first 15 minutes. And so we can calculate this by just going ahead and using our equations that we've learned so far in our study of one-dimensional kinematics. So first thing I'm going to do is I'm going to remember that when v is constant, my instantaneous speed v is equal to my average speed, v average. So in this case, this would be up until my t equals 15 minutes. So that's up until this time right here. In that period of time, I would have traveled delta x over delta t, right? That's my displacement over change in time. So I can go ahead and rearrange this equation and get my displacement, delta x, is going to be equal to v delta t during that time frame, where v is my average velocity, but it's also equal to that instantaneous velocity. In this case, it was 1 mile per minute. Okay, so plugging in 1 mile per minute, we're traveling over 15 minutes, and so that tells me that I have traveled 15 miles east, right? Because my minutes would cancel from the numerator and the denominator. And east is telling me the direction of my velocity. Since it's a velocity, it always needs to have a magnitude and a direction. Okay, so that's the first part. So how far did you drive during those first 15 minutes? Now we want to look at our graph, and we want to know what is the area under the v versus t curve from t initial equals 0 minutes to t final equals 15 minutes. So what is the area under the curve all the way along here from 0 up until 15? So what is that area in there? And so we can actually go ahead and calculate that out. I have it drawn in more nicely with a little square here. So what is the area of that rectangle? That's basically what we're asking. That's what it means when we say the area under the curve. It really just means the area between my plot and the axis, the x-axis, or t-axis, right? The horizontal axis there. Okay, and so how would I calculate that out? Well, the area of a rectangle is just base times height, right? So height times width in this case. So what is my height? Well, the height would be this distance right here, which I would say is going to be 1 mile per minute. And what is my base? My width? It's going to be 15 minutes, right? So that's how I would calculate out the area of that rectangle there. So 1 mile per minute is my height, 15 minutes is my width. You multiply those together, the minutes cancel, and you're left with 15 miles. And it's positive, which we said was the east direction. So the area of the rectangle, you can see, was exactly equal to the displacement during that time frame. And we did it during this lovely rectangular portion of the graph because that's nice and easy to calculate area, but it's actually true in general. So we always find that the displacement is equal to the area under the v versus t curve over the time frame during which you want to calculate that displacement. Okay, so let's just go ahead and summarize that. Here I have another velocity versus time curve. And I want to think about two different things when I'm looking at these v versus t plots. First of all, the acceleration at a given point in time is equal to the slope of that v versus t curve at that moment in time. So if I pick some time, like here, it looks like this is my time of interest, then the slope at that moment in time would be equal to the slope of the tangent to the curve at that point in time. Next, the last piece of information that we just learned is that the displacement over a particular time interval is going to be the area between our curve, right? So that's this guy, the curve, and the horizontal axis or the time axis during that particular time interval over which we want to calculate the displacement. Okay, so how do I calculate that area? Well, here I've drawn in some blue rectangles. And say we want to calculate the area or the displacement from some initial time right here, this guy, to some final time over here, t final. Okay, well, so then to calculate that displacement, what I could do is just calculate the area of that blue rectangle. So this particular rectangle right here, that's the area underneath the curve from t initial to t final. And so then I would see that that area under the curve is delta t multiplied by a height v. Here we can approximate that it's nearly constant right here. It's a little bit upward. It's a little bit of a positive slope, but it would be nearly constant at the top. And so I could use an approximation of the constant value of the velocity or the height of that rectangle to calculate then the displacement using the area of that rectangle, which would be the height v multiplied by the width of the rectangle delta t, to get the displacement delta x. Okay, and so let's just go ahead and check the dimensions of this equation, v times delta t equals delta x. Well, v is velocity, so it has dimensions of length divided by time. Time has dimensions of time, and that's equal to displacement, which has dimensions of length. So here I would see that these two time dimensions cancel, and I get length equals length. So this does work from a dimensional analysis point of view. Okay, and so in general, how am I going to calculate this displacement? What you need to do is break the area up, the area under the curve over the time interval in which you're interested in finding the displacement. You want to just break that up into pieces for which it's easy to calculate the area. So in general, those pieces should be shaped like rectangles or triangles because we know how to calculate the area of both a rectangle and a triangle. So just a refresher, rectangles have area of width times height or base times height. Triangles have area of 1/2 width times height or 1/2 base times height. Okay, so that's what you'll want to think about is splitting up that area under the curve between your initial and final time into shapes that are easy to calculate the area. So let's go ahead and do a practice problem for this. So we have a given velocity versus time plot, and we want to know the displacement between times A and B. So before you get started, I have a few hints, a few tips. First of all, we need the area, remember, between the curve and the time axis. And with that in mind, we need to remember that velocity and displacement are vectors. And so we need to include signs, right? So remember vectors, we need to think about magnitude and direction, which means that those signs, plus and minus signs, come into play here. They are important and we do need to include those. Okay, last thing to remember is that the area of a triangle is 1/2 width times height. Okay, so go ahead and try it out. All right, let's see how I went ahead and solved this problem. First of all, I remember that the displacement between A and B is the total area under the curve, so between the curve and the time axis from A to B. So I would say that the first part I'm going to break up into a triangle, right? So that would be from time t equals 5 to time t equals 6. And so I have this nice triangle. It has a height of 1 meter per second. Looking at my axis over here, I would say that that's 1 meter per second. And it has a width across the bottom also of 1 meter per second, or of 1 second, right? And so that would be the width of my triangle. And so then the area of that green triangle is 1/2 1 second, that's the width, times 1 meter per second, that's the height. And so then my seconds cancel and I'm left with 0.5 meters for the area of that first green triangle there. Okay, next I need the second piece of area between the curve and the time axis. So I would actually go ahead and draw in a second triangle. This time it's upside down, right? And so my elapsed time, again, this is going to be from t equals 6 seconds to t equals 7 seconds. And so then I would still have a base or a width of 1 second here. My height, remember I need to include signs. So my height is really going to be -1 here, right? So that's 1 block on my graph. So the area is 1/2 of 1 second times -1 meters per second. My seconds cancel and I'm left with -0.5 meters. Okay, so then the total area under the curve, or the displacement, is just going to be the area of the green triangle, which is 0.5 meters, plus the area of the blue triangle, which is minus 0.5 meters. And so I get that the displacement over this period in time is 0 meters. Okay, next up, I just have a quick warning. It's about calculating this displacement. So it turns out that, we learn that the average velocity is equal to displacement over change in time. And this is always true. However, in many problems, you do not know the average velocity. So it's really tempting, if you're given a velocity at a particular point in time, to just plug it into this equation to calculate the displacement. But in general, that velocity that you're given is an instantaneous velocity and not an average velocity. And so you're not going to come up with the right answer, because those two things, they're not equivalent to each other. Okay, and so what that means is if v is changing, we need to be really careful about how we relate the acceleration, the velocity, and the position, or the displacement. Okay, and so how do we go about doing that? We use the equations of motion for constant acceleration. Okay, and so we have some simplified notation that allows us to write out these equations. First of all, we always say that the initial time is time t equals 0. That's just a simplifying way to solve these problems. So always your initial time is time t equals 0. Then your position at that initial time, which we've been calling x initial, we just call that x naught. So the naught really just means at time t equals 0, or at the starting time. Then we also define the initial velocity as v naught. So those are both the velocity and the position at our initial time, which we've set to t equals 0. Okay, then we also use the simplifying notation. Since we know that x naught and v naught are our initial positions and times, then we just use the simplifying notation that our final position, we're just going to call it x, and our final velocity, we just call it v. This is an instantaneous velocity, by the way. Okay, so, and then we also say that our final time is just t. All right, so that just cleans up the equations a little bit. It just helps us to drop some of those, it helps us to drop some of the subscripts, which can get a little overwhelming. All right, so with those simplifications, we can derive these 5 equations of motion for constant acceleration. To see how these are derived, you can see the supplemental class 5 video. Okay, so here I have my 5 equations, and they all come from the basic equations we've already learned. Displacement is just change in position, which I've plugged in. Our new notation here would be x minus x naught. Average velocity is displacement over change in time, and acceleration for constant acceleration is just going to be change in velocity over change in time. Okay, so these 5 equations, they all come from the basic 3 equations over here. I've just manipulated them so that we have convenient ways to solve for the information that we're looking for. Okay, so first of all, for these 5 equations, I'm just going to go through and mention the things that are related. So first equation, v is equal to v naught, our initial velocity, plus the acceleration times time. So we have velocity, acceleration, and time. Next, we know that the average velocity when we have constant acceleration is just equal to the sum of the final velocity v and the initial velocity v naught divided by 2. This is only true when we have constant acceleration. Position, velocity, and time. So my final position x is equal to my initial position x naught plus 1/2 of my final velocity plus my initial velocity multiplied by time. Second to last equation here, position, initial velocity, and acceleration, as well as time, are all related through the equation final position x equals initial position x naught plus initial velocity multiplied by time plus 1/2 the acceleration times time squared. This guy is the big guy. We're going to use that one quite a bit. So this is definitely one to remember. We are often given initial conditions, which would be the initial position and the initial velocity, as well as the acceleration. So this equation is really probably the most useful to us. All right, last one here, position, velocity, and acceleration are all related through the equation v squared, final velocity squared, equals initial velocity squared plus 2a times displacement. Okay, and this one is also really very useful because you'll notice that it doesn't have anything, it has no mention of the final time, right? So it has no mention of t. And so if you are given a problem where you are not told any information about the amount of time over which, these measurements are being made, then you'll want to use this equation. Because if you don't know it and you don't need to know it, then this is going to be the equation you want to use since you don't have to know the final time to use this equation. Okay, a few notes here. Don't memorize these, please. You will be given an equation sheet, so I don't want you to waste your time memorizing these. I would recommend writing them out and having them on a piece of paper that's always near you when you're solving these types of problems, but you do not need to memorize them. There are many ways to solve most problems, so you could use a combination of these equations to solve most problems. However, there's usually one easiest way to do it. So if you don't pick the easiest way, it's not a big deal. You'll just have to do a little bit of extra work. You can still get the right answer. The way to pick the easiest way to solve the problem is to look at these 5 equations and look at your list of knowns and your unknown, the thing you're solving for. A lot of the times you'll be able to find one equation that gives you the one thing you don't know that you're looking for, and everything else in that equation is something that you know. And that's going to be your easiest way to solve the problem. Now, if that's not the case, you might have to use 2 of these equations to solve for one unknown, and then use that unknown in another equation to solve for the final thing you're looking for. But most of the time, you should be able to look at these equations and find one that has only one thing you don't know, and that thing is the thing you're looking for. Okay, and then in this class, we will always, I'm not going to say almost, the acceleration will always either be constant or 0, which means that you can always use these equations. And so that way you can use these equations and you can solve for displacement. Remember, I mentioned that solving for displacement can be a little tricky. And so you can use these equations to solve for displacement without using the hazardous delta x equals v average times delta t, for which it's really tempting to plug in any value of velocity when really that value might not be the average value, right? So we don't have to worry about, is this my average velocity? Is it not my average velocity? So we don't want to use that equation, delta x equals v average times delta t, unless you're really sure that the velocity that you've been given is the average velocity. Instead, you could use one of my 2 starred equations here, and that should lead you on the right path towards finding your displacement. Okay, and that's it for today. I will see you in class.